All right, it's time to do some example problems from chapter 10. And again, I just have a few problems that I've selected that we're going to do together in this video, and the solutions to the rest of them should be showing up on Blackboard for you. The first problem we're going to do is number 1 from chapter 10 in your textbook, and it says, prove the mapping given in example 2 is a homomorphism. So the mapping given in example 2, if you go back and look at it, is phi of A equals the determinant of A. And we are mapping the general linear group 2 by 2 matrices with real entries to the reals under multiplication. So if we're trying to show that this mapping is a homomorphism, we need to show that this is operation preserving. So we need to show operation preserving. So operation preserving means that we have phi of A times B needs to equal phi of A times phi of B. So let's start with phi of A times B. Oh, that is not what I wanted to do. There we go. Phi of A times B. Well, this equals the determinant of A times B. Well, we know some things about determinants. We know the determinant of A times B is equal to the determinant of A times the determinant of B. That's a fact that you should know from linear algebra. Well, wait a second. Isn't the determinant of A times the determinant of B equal to phi of A times phi of B? And that's exactly what we wanted it to equal to show that it's operation preserving. So therefore, we're able to say, therefore, phi is a homomorphism. Woohoo! That was a nice quick one to do. Our next problem that we're going to look at is number 3. Number 3 says, prove that the mapping given in example 4 is a homomorphism. So we've got to think back, what is the example 4 talking about? So this is example 4 from your book. Example 4 from your book gave you the mapping phi of f equals f prime, the derivative of f. And we're mapping from the polynomials with real coefficients under addition to polynomials with real coefficients under addition. So again, if we're trying to show that this is a homomorphism, we really just need to show that this is operation preserving. So to show operation preserving, we would need to show that phi of, let's say, f plus g, not times because we're under addition, so f plus g is equal to phi of f plus phi of g. So that's what we need to show. Let's see if we can do it. So consider phi of f plus g. Well, that would equal the derivative of the sum of these two functions. But when we're thinking about derivatives, really the derivative of the sum of two functions is the sum of the derivative of each of the functions. But this is just phi of f plus phi of g, which is exactly what we were trying to show. Therefore, we've shown that it's operation preserving. Therefore, phi is a homomorphism. So the first two problems went pretty quickly. Whenever we're trying to show that something's a homomorphism, we only need to show operation preserving. So number 14, we get a slightly different task. We get the task of showing that something is not a homomorphism. Now this looks fairly similar to one of the problems that we did in our video lecture, where we had phi of x equals 3x, and we were mapping from Z12 to Z12. And that was a homomorphism, but now when we're mapping x to 3x, going from Z12 to Z10, this is not a homomorphism. And if we're asked to explain why, well, we have to show that the operation's not preserved. So we need to show that operations are not preserved. So we want to pick two things in Z12 that we are going to add together to map to Z10. And we want to pick these things carefully. Two things that I think that we could use would be 6 and 7. So we're going to look at phi of 6 plus 7. Now, 6 plus 7 is 13, which if we were still in Z12, this would be equal to phi of 1. Phi of 1 would be 3. Now, to show that it's not operation preserving, we need to show that phi of 6 plus phi of 7 is not equal to 3. So let's see what it is equal to. So phi of 6 would be, let's see, that'd be 3 times 6 is 18, and phi of 7 would be 3 times 7, which is 21. And now that we've done the mapping, we're in Z10. So that means we have 8 plus 1, which is 9. And 3 is not equal to 9. So that tells us that phi of 6 plus 7 is not equal to phi of 6. I'm running out of space here. Let me rewrite this. So 3 does not equal 9. So that tells us that phi of 6 plus 7 does not equal phi of 6 plus phi of 7. So this is what's showing us that it's not operation preserving. Now, you could show this with two elements from Z12 that are not 6 and 7, and it might be a good exercise for you to find two elements besides 6 and 7 that you could use to show that it is not operation preserving. All right, number 15, suppose that phi is a homomorphism from Z30 to Z30, and the kernel of phi is equal to 0, 10, 20. If phi of 23 equals 9, determine all elements that map to 9. Now, in order to do this, we're actually going to use a theorem. We're going to use theorem 10.1, item number 6. Now, what this said is it said that we can know everything that maps to an item by using our kernel. So it allows us to say phi inverse of 9 equals 23 plus the kernel of phi, well, the kernel of phi is 0, 10, and 20, so that means this would be the set. 23 plus 0 is 23, 23 plus 10 is 33, and 23 plus 20 is 43. Only we are working with Z30 here, is what we've mapped. We are talking about this Z30 here. And so we want to take it mod 30. So we would have 23, this would be 3, and 13. So if you wanted to, you could rewrite it so that you said 3, 13, 23. So this is the set that maps to 9. And all we had to do there was just use that 6th property of theorem 10.1. So this is an example of why we need to know those properties and have those properties handy when we are trying to do proofs. All right, one more problem, and then I'm going to let you try all of the other ones on your own. Reference the answer key, and then of course let me know as you have questions. If phi is a homomorphism from Z30 onto a group of order 5, determine the kernel of phi. Well, for this one, we are going to use a theorem again. We are going to use theorem 10.3 as we work this problem. And from this theorem, we know that the order of Z30 divided by kernel of phi equals 5, which tells us what? Well, that tells us that the order of the kernel of phi has to be equal to 6. Now, the kernel of phi has to be a subgroup of our group, right? Well, there's only one subgroup of Z30 that has order 6. So, kernel of phi must be a subgroup of Z30. Only one subgroup of Z30 is order 6. And that subgroup is the cyclic subgroup generated by 5. So that means that we know that the kernel of phi has to be equal to the cyclic subgroup generated by 5. All right, so that's it for our example problems from chapter 10. Again, if you have questions, shoot me an email. I am more than happy to talk to you and work through some problems with you. Continue to work hard. You guys are doing great, and I'll see you in chapter 11.